before we look at graphing in 3 dimensions, I want to look at graphing in 2 dimensions using intercepts, because we're going to use a similar idea for graphing in 3 dimensions. So if you actually already know how to graph something like this by using x and y intercepts, you may just want to skip ahead to the example in 3 dimensions. If you don't know how to graph this by using x and y intercepts, probably follow along here. So let's look at the x-axis here. So highlighted in green, that is the x-axis. So if we want to find, say, where this line crosses the x-axis, well, let's think about what the y value will be. So if we're on that green line, the y value is 0, because we're not any bit up or down. Y tells you how far you are up or down, so we're not up or down at all. So if we plug in 0 for y, we can find where it will cross the x-axis. So let's do that. Negative 3x plus 5 times 0 equals 15. Well, 5 times 0 is 0, so that'll go away. Negative 3x equals 15. Divide both sides by negative 3, and we get x equals negative 5. So that's a coordinate point. We plugged in 0 for y, and then we got negative 5 for x. So that's the coordinate point, negative 5, 0. So we found the x-intercept. We found the place where the graph crosses the x-axis. We can do the same thing for the y-axis. So the x value on the y-axis here, on this red line, the x value there is going to be 0, because x tells you how far you are left to right. And so if you're right on the y-axis there, the x value is 0. So if we plug in 0 for x, then we can find the y-intercept. So this goes away. 5y equals 15. Divide both sides by 5, and we get y equals 3. So here we plugged in 0 for x, and then we got 3 for y. That's another coordinate point. And there's the y-intercept. Now we can graph this line just by drawing a straight line between those 2 points. So when we look at graphing it in 3 dimensions then, well, now we have 3 different variables, 3 axes. Instead of just an x and y axis, we also have a z axis. Now, when we're trying to graph in 3 dimensions on a 2-dimensional surface, so this board here is a 2-dimensional surface, your piece of paper is a 2-dimensional surface, and so when we try to graph something in 3 dimensions on a 2-dimensional surface, it doesn't work so well. So you can see that we've got what looks like the normal xy axis, but then we also have this diagonal axis here. So it shouldn't actually be diagonal. We just kind of have to represent it diagonally, because we can't take 3 dimensions and condense it down into two dimensions without losing information. But think of this like the corner of a room. So if you look at the corner of a room, you have kind of one wall meeting with another wall, meeting with the floor, and that point where all 3 of those meet, there's this one point where the 2 walls and the floor meet, and think of that as the point 0, 0. So all these axes should have right angles between them. We just can't really do that in 2 dimensions. So we kind of have to pretend. But we can do something very similar to what we just did. So say that I want to find the x-intercept. So I want to find where this graph crosses that red line. Well, that's going to be not only where y is 0, but also where z is 0. So if I think about trying to find the x-intercept, I'm going to plug in 0 for both if I want to find the x-intercept, I'm going to plug in 0 for both y and z. So then we'd have 2x minus 3 times 0 plus 4 times 0 equals 12. All this stuff goes away. We get 2x equals 12, so then x equals 6. So what happened there is we plugged in 0 for y and 0 for z, and we got 6 for x. So let's plot this on the x-axis. 1, 2, 3, 4, 5. I guess I'll have to extend it a little bit, but there is 6. There's the x-intercept. Now let's find, how about the y-intercept? So the y-intercept is going to be where x and z are 0. So let's plug in 0 for x and for z. Two times 0 goes away, 4 times 0 goes away. We end up with negative 3y equals 12. Solve that by dividing by negative 3, and we get y equals negative 4. So for this one, we plugged in 0 for x, we plugged in 0 for z, and then we ended up with -4 for y. So on the y-axis here, we got to be a bit careful about which way is going which way. So you see here, this side is -y, this side over here is +y. So if we're looking for -4 on the y-axis, we're going to have to go up this way 4 units. That'll be right there. Now there's one more axis, it's the z-axis, that's the up and down axis. If we want to find that intercept, that's going to be where x and y are 0. So plug in 0 for x, plug in 0 for y, and then solve for z. So 2 times 0, 3 times 0, those go away. So we get 4z equals 12, divide by 4 to get the z-intercept. So there we plugged in 0 for x, plugged in 0 for y, and got 3 for z. So that's going to be right here. All right, now again, we kind of have to pretend here because it's pretty difficult to kind of imagine what's happening here without seeing it in actual 3 dimensions. But kind of think of a plane. So this graph, when we have 3 variables here, it's going to be this 2-dimensional plane, this flat kind of sheet. So think of maybe like a piece of paper or something else that's flat, that's going to be resting on these 3 intercepts. And it will extend in all directions, but what we're going to do to represent this is just kind of draw a triangle here between the 3 intercepts. So imagine this kind of flat sheet of paper resting on those three intercepts there. But again, what we do, because it's the best we can do without actually having some sort of holographic 3-dimensional graphing thing, the best we can do is kind of just put the intercepts there, draw a triangle there to indicate that this is the angle of that flat sheet, and then just leave it at that. That's the best we can do here with only having 2 dimensions.